All right. So what we have going on here is, all right, we're getting into Coulomb's law and electric fields. So for today's assignment, we're going to do both things. We're going to do Coulomb's law and electric field lines. That's all we're going to kind of get into. So really quickly, just going to kind of go over what's going on here. So the symbol for electric charge is a capital Q or a lowercase q. The unit for electric charge is a Coulomb. Now, Coulomb is pretty big. It's a pretty large amount of charge. All right, it's the charge that comes from 6.25 times 10 to the 18th electrons. So quite a bit of them, and their charge. So 1 Coulomb of charge is actually quite big. So a lot of times you may see this symbol, which is a micro. So the Greek symbol mu, a microcoulomb. So 13 microcoulomb. 1 Coulomb is basically a million microcoulombs. So pretty much we divide that out by a millionth. So 13 microcoulombs is 13 millionths of a coulomb. And you're going to get that. So I think on most of the stuff I've already converted everything into coulombs for you, so you may see a couple exponents here or there. All right, so 3 factors that determine the magnitude of the force between 2 charged objects is the charge on the objects, the distance between them, and the material that is separating them, whether it's air or an insulated material. Okay, so the force between any 2 charges, all right, Coulomb's law, which is what we're going to talk about. So the force between any 2 charges depends directly on the magnitude of the charges and is inversely proportional to the distance squared between those 2 charges. So the equation is the electric force is equal to K, Q1 times Q2 over D squared. Sometimes you may see it as R squared. All right. K is the constant, just like we had in the universal gravitation equation. You had big G there. Now, for this, it is for air. This constant is 9 times 10 to the 9th Newton meter squared over coulombs squared. All right. So if both of your charges are positive, the electric force is that you calculate out is positive, which means 2 positives, what do? Like charges repel. All right, if they are both negative and the answer comes out as the electric force is positive, that would also be a repulsive force. If, all right, one is positive and one is negative, all right, the electric force will wind up becoming negative, and that means that they will be attracted. All right, we will get into Coulomb's law in a hot minute. All right, again, like I said, it was kind of similar to Newton's law of universal gravitation. If you look at the equations, they're pretty similar. All right, gravitational force, electric force, charge 1 and charge 2, mass 1 and mass 2, divided by the distance between their centers squared, and then they have different constants. They are inverse square laws. All right, the values of their constant definitely differ. K is 9 times 10 to the 9th. Big G is 6.67 times 10 to the negative 11th. All right, gravitation, all right, universal law of gravitation. Gravity is an attractive force only, where the electrostatic force, okay, can be repulsive or retractive. All right, repulsive or retractive. Now, both electric and gravitational forces are field forces because objects do not have to touch to be subjected to the force. So for the simplisticness of our drawing, which will be on our assignment today, which will be on your test, and you'll also see this on your final exam, all right, a positively charged little test sphere here, all right, is going to have arrows pointing away from positive charge and towards negative. All right, the spacing of the lines show how strong the charge is. So this is a not super strong, much stronger. All right, based off of the number of arrows. All right, the more amount of arrows, the stronger it is. The closer they are, the stronger it is. We generally want it to be evenly spaced if it's just a kind of charge sitting and chilling as is. All right, for the most part. And then The negative charge, all right, the arrows point into it. They end on a negative charge. They radiate out from a positive charge. So if you saw these two covered out, you see arrows coming out of the left side. You see the arrows coming out of the left side one. We could say that, okay, that's definitely positive. They're going into the right side one. That is negative. All right, two positives, they'll radiate outward, but as these two get closer together, all right, those field lines kind of bend and repel away from each other. They're not going to cross. All right, they will not actually cross. All right, that is important to know. Field lines will never cross. All right. Okay. Right. We're not going to get into the rest of that. So pretty straightforward if we take a look at this. Now this comes mostly off of our physics classroom website. All right, we have going to look at several different diagrams, so you guys should have this paper out in front of you. There are several different diagrams. All right. Yep. Nope. We're passing it out right now. All right. So just lock in. Pay attention now. Okay. So on this, several electric field line patterns are shown in these diagrams. Out of these, which patterns are incorrect? So which patterns are incorrect? So we said the field lines come out of the positive charge, go into negative charge. All right. E is one of them because, right, it's radiating out. So E is one, and why? Because, all right, lines go towards negative charge. Is D1. D is 1. Why? All right, we have E, we have D. D is because, right, the lines should be evenly spaced. The lines should be evenly spaced. I can't spell today, but you know, you get the point. Is there anything else? So we have D, E, what else? There's one other one that's wrong. Come out of positive charge, go into negative charge. So which other one would be wrong then? C. Yes. Why? Because, all right, field lines should come out of the positive charge. All right, so in this one, Mr. Lombardo, in his haste, drew the following electric field lines for a configuration of two charges. What did I do wrong? I mentioned it briefly. So think of it almost like this, guys, right? Positive charges do what to each other?
To each other?
Repel.
Positive, they repel.
Okay. Is this fully repelling then? Right here? No. So why is this wrong? Because the field lines should never cross. Okay? The electric field lines should never cross. All right, now, in number 3, we have this picture here. It says, consider the electric field lines shown in the diagram below. From the diagram, it is apparent that object A is blank, question mark, and object B is blank, question mark. Can you tell what charge is what? based off of our rules?
A is positive, B is negative.
Why is A positive and B negative?
A is positive because it's like sucking in
All right, so go back to our top. Go back to the top. Field lines. Yes.
A is negative, B is positive.
Correct. Okay. So biggest things you need to know. All right. The field lines radiate out from positive charge, and they end on negative charges. So here you can see the arrows pointing out, generating out from this, which means that this dude should be positive. All right, and then they end on negative charge. So this dude here will be negative. All right. Okay. Next one. Oh, this is it. I love this. Really quickly, we're just going to figure out, hey, which one's positive, which one's negative. A, are they going in or going out?
Going out.
Going out, so going out would be?
Positive.
That's correct. All right. B, are they going in or out? Which means?
Negative.
Yes. All right, look at C.
C is positive.
C is positive. All right, radiating outwards. What about D? Negative. Good. What about E?
E is negative.
E is negative because they're, all right, going in. And what about F?
Positive.
Correct. What about G,
All be
H, and
positive?
they are all positive. Correct. Very, very good. All right. G, H, and I, they are all positive. All right. All the arrows radiating out. All right. So that's simple. That we're not gonna. There's an equation to calculate the strength of an electric field lines and the test charge involved with it. All right. We're not going to get into that level right now. We're just going to deal with the simplicities. All right, and the little basics here for this. Okay. So determining which kind of charge it is, right? If it's positive, negative, and then we have to also determine, like in this one, all right, out of the electric field lines, rank them by which one has the greatest magnitude of electric charge. All right, so we're going to say which one is the larger charge. The larger charge will go to the right, so weakest to largest. Who is weaker? Wait, I'm not really sure. How do we do this? So in the little notes things that I kind of handed out to you guys. All right. The more arrows coming out of a charge, the stronger it is.
So B is a lot less than A.
Yeah, correct. B does not have as many lines, all right, as A, so A is the stronger, B is the weaker. This one should be pretty obvious. Who's stronger here? D. And C is our weaker. We're going to zoom in a little bit for these two. All right, let's look at this one first. Who's definitely the strongest?
The middle.
F, yep, the middle.
F is the strongest, E is the second, G is the third.
How many people agree with that? Yeah, I would as well. G has like the least amount of field lines, so G would be the weakest, and E would be our middle. My name is Jeff.
Oh no.
All right, never mind.
We can still make you smile, Mr. Lombardo.
Yes. Oh boy, who's the strongest one here? Yeah, definitely I. How many people concur? I would as well. JHI. All right, so that is our electric field lines. All right. Later on this week, you guys will have an electrostatics test review. All right, and then 2 classes from now will be our electrostatics test, and then we'll get into circuits. All right, we're not going to go into crazy details, but we're going to get into them. All right, so now we need to go into Coulomb's law. All All right, now we're going to get into Coulomb's law. So that's going to be this this paper here. All right. So on this paper, which is coming to you guys right this second. Okay. We are going to, all right, take a look at these. So again, Coulomb's law, when you are solving for it, all right, in totality, which would be an example on the back side, okay? These would be some normal problems. You have Coulomb's law equation, K, Q1, Q2, which is the charge of the first and second object and the distance between them squared. All right, K is the constant, which is 9 times 10 to the 9th Newton meter squared over Coulomb squared. All right, that is what you have to, definitely make sure you have everything that you can throw into a calculator, all right, with your exponents and everything like that. All right, but what we are going, so you will have like a problem or two like that on your test, but you will have more problems that are going to be like these guys here, proportionality type problems. So since K is a constant that does not change, we are going to kind of ignore it in the proportionality portions. So Q1 and Q2 are your charges. All right, they go on top. They're going to be represented by the number 1. And distance between them, all right, squared, all right, we're going to make the distance a 1 as well, and we got it squared because that is what we do. So it's the product of the charges divided by the distance between them squared. So I have a full worked out example. You have two charged objects. They have a repulsive force of 0.08. So if it's repulsive, both charges have to be either positive or both charges have to be negative. Okay? Because that's why it's repulsive. If they said attractive, one charge would have to be positive and one would have to be negative. Okay? So when looking at this, all right, we set this up. Charge of the first, charge of the second over the distance squared. So the first one says, all right, if the charge of one object is doubled. So the top ones are our charges. They're going to say just one of them doubles. So it doesn't matter which, but I just picked the first one. I turned that into a 2 because it said this thing doubled. And they didn't tell me to change anything else. So because of that, I'm keeping this dude a 1, and they didn't tell me anything about the distance, so I'm keeping that a 1. And then you just kind of play this out. 2 times 1 is 2, divided by 1 squared, which is just 1, and you would have double the amount of force. If the original force is this 0.08, I'm doing 2 times 0.08, which comes out to be 0.16 newtons. Now here it says, again, the beginning starts the same. So this is our charged object. Now it says if the charge of both of them is doubled, what are we going to do, right? We still have our 1 times 1 over 1 squared. If both, all right, charge of both is doubled, both my charges are going to become 2. 2 times 2, they didn't tell me anything about the distance, so I leave it as a 1. And I play this out. 2 times 2 is 4. 4 divided by 1 squared is 4. So it would be 4 times the force. And then we're just going to multiply that by the original value that they gave us. And this comes out to be 0.32 newtons. And then they kind of talk about, all right, how does this change around with the changing of distances? So with distances here, you have charges of the guys on top, 1 and 1. All right, distance on bottom, chilling. All right, this time they said the distance, all right, between them is doubled. Nothing happened with the charges, so 1 times 1 on top over, since distance is doubled, you have to make that 1, that's the distance, a 2. Now, it is squared in the equation up top, so you still have to square that. 1 times 1 is 1, 2 squared is 4, so we'd have 1/4 of the original force. And then 1/4 of 0.08 comes out to be 0.02 newtons. Now they said, hey, cool, awesome, if the distance separating them triples, what's good? Well, nothing happened with the charges, but the distance is now 3. But you still have to square it. 1 times 1 is 1, and 3 squared is 9. So you'd be 1/9 of the original force. So 1/9 times 0.08. When you throw that into a calculator, all right, comes out to be 0.0088. It may be 88 repeating. I don't have my calculator right down in front of me. Thank you. So if you did 1 divided by 9, cool, you can hit enter, and then just multiply that by 0.08. Yeah, all right. So if we round it to 2 decimals, it could be 0.0088 or 0.0089. If we're just cutting it to 2 decimals, either one is fine. All right. The next one, distance is quadrupled. What does quadrupled mean, y'all? 4, right? Anything happen with a charge? No, they didn't say anything about charging. All right, or the charges. So 1 times 1 on top. Distance is now 4. What's 4 squared? Anybody? 16. So be at 1/16 the force. All right. So we're going to take that and times it by the original force of 0.08. And it kicks out to be exactly 0.005 newtons. Why is it newtons? Because it's an electrostatic force. All forces are measured in newtons. Okay. Gravitational force and electrostatic force, applied force, all that stuff, all that good stuff. All right, now here 2 charges again. This time the distance is halved. What's the new force? Halved. All right, well, nothing happened to our charges, but the distance got cut in half. So 1/2, and then I have to square that. So this one, I would definitely suggest throwing it into the calculator, right? 1 times 1 is 1 on top. All right, cool. So let's then do 1 divided by 2 squared, close it, boom. This becomes a 0.25. Now I gotta actually throw this into the calculator. 1 divided by 0.25 comes out to give me 4. 4 times the force. And so we gotta do 4 times 0.08. And that will come out to give us 0.32 newtons. Okay, so when you get closer together, what did you see happen? And what do you see happen as they get further apart? Okay, when the distance doubled, we went from 0.8 to 0.02, right? We doubled the distance, we went to 4, right, 1/4. Why? Because it's the distance squared. So when this number becomes larger, all right, the overall force is going to become less, right? Sorry, we're on this one. We're looking at the distances, right? The charge is very simple. You double one charge, you double the force. You double both charges, it's quadruple. If you did 2 times one charge and 3 times the other, 2 times 3 is 6. It would be 6 times the original force. For distances, if we increase the separation, right, the farther apart they are, I know it's not the exact same, but almost think like magnets. When you separate magnets, right, they get really weak as they get further apart. As they get closer together, all right, the force increases. So if the force was originally this, we separate the distance, all right, make it double, it decreases by 4 times. If we increase the distance by triple of the original, it, all right, goes down 9 times, all right, it's 9 times as less, 1/9 as strong. If you increase the distance of separation to 4 times the original, now it's 16 times less. What would it be if we did 5 times the distance? What's the pattern? It's the square, right? 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared would be, it'd be 1/25 the original force. So that is how that works, all right? And vice versa, if you, all right, decrease the distance between them, right? They get closer together, you're going to see an increase in the actual force. All right. Now this next piece is doing a combination of charges and distance. All right. So what's good here? If the charge, one object is doubled, right? So again, this is how we're starting out. Charge of the first, charge of the second, distance. So they said one charge is doubled. So I'm going to make one of them a 2. Nothing about the second charge. Over, and distance is doubled. So the distance, which is on bottom, I'm going to make that one a 2, but I have to square it. 2 times 1 is 2. 2 squared is 4, which just reduces down to 1/2 of the original force. So half of the original 0.08 comes out to be 0.04 newtons. All right, now what's good? What are they telling us here? Charge of both objects doubled. So the two, all right, ones on top that are charges. All right, it says they both double. So instead of ones, they're both going to be 2s because they both doubled. And the distance is doubled. So the one that's on bottom for distance, we got to turn it into a 2, and you have to square it. 2 times 2 is 4, and 2 squared is 4. 4 divided by 4 is just 1. So it'll be 1 times the force, or just 1 times 0.08, which is, yeah, pretty much the same answer. All right, anything times 1 is going to be itself. Next one, charge of one of the objects is increased by a factor of 4, and the distance is doubled. So now what's the new force? Well, one of the charges increases by a factor of 4. We're going to turn it into a 4. They don't tell us anything about the second charge, so that stays a 1. But the distance, all right, doubled. So the 1 on bottom for distance, we got to make it a 2, and when we square it, all right, we play this out. 4 times 1 is 4, and 2 squared is 4, which reduces down to 1 times the 4, so it's going to be the same answer as, all right, the one just above this. So on your test, you're going to have a few of these. They're going to have a combination of a couple. They're going to tell you, hey, the charges are doubled or tripled, the distance is doubled, or the distance is tripled, or it's cut in half. What is the new force going to be? And they'll give you like a number to start with. So here, 2 charged objects have an attractive force of this. If the charge of one object is tripled and the distance is tripled, what's happening? Well, one of the objects is tripled, the other one didn't change, and the distance is tripled. So D on bottom becomes a 3, and you have to square it. What is 3 times 1? It's 3. 3 squared, 9. 3/9 reduces down to 1/3 of the force. So if we do that into our calculator, okay, 1 divided by 3 times 0.08, all right, we come out with this 0.02666666 repeating. So we'll cut it up at 2 decimals, so 0.026, but we can round that to a 7. All right, if we round that to like 2 non-zero decimals there, and boom, newtons. All right. So you will have some problems like that for sure on your test, and probably at least one of these guys on your final exam. And then this last one, this last little section, all right, is now just using the actual numbers from my problem into the equation. So I'm just asking you guys to solve for the force. not ask you to rearrange and solve for the distance, in which case d squared and f would swap places, and then you would have to square root both sides of the equation. All right, or rearrange and solve for the magnitude of a charge. We're not doing that. All right, we're pretty much going to keep this thing nice and straightforward. So in this case, a balloon that had a static charge of 4 times 10 to the negative 5th coulombs was held at a distance of 0.10 meters from a second balloon having the same charge. Calculate the magnitude of the repulsive force. All right, so I wrote, hey, both Q1 and Q2 would be the same. Why? Because they said that the thing has the same charge. So the first thing they came up, that's just arbitrarily going to be charge 1. Boom, write it in. Same charge, so Q2 is going to have the same. The distance separating them was 0.10 meters. All right, and then that's our Q1, Q2, and D. K is always going to be this number, 9 times 10 to the 9th, and then we plug and chug. So in this case, the next one, calculate the electrical force in newtons exerted between a 22 gram. Do we need to know the mass of this thing in order to figure out the electric force? No, we don't see a mass in here, so that's actually kind of irrelevant. We don't need that. So, all right, it has a charge of negative 2.6 times 10 to the negative 6 coulombs, so I'm going to write Q1, negative 2.6 times 10 to the negative 6th coulomb. Q2, the second charge, in this case it's the charge of the sweater, which is a positive 3.8 times 10 to the negative 6th coulombs. And they are separated by a distance of 0.75 meters. So we have Q1, Q2, and D. K always comes first, and K is this 9 times 10 to the 9th. So I'm starting that off. 9 times 10 to the 9th times Q1, which is negative 2.6 times 10 to the negative 6th, and times that by 3.8 times 10 to the negative 6th. All of that will be divided by the distance between their centers squared, which is 0.75. Boom. And so then we just need to throw this into a calculator. All right. So in your calculators.
Hold on, Mr. Lombardo. Can you hold on 2 seconds?
Yeah. Well, I'm just going to show you guys. Right, if you're going to use the times 10 caret symbol like that, that's fine. Just make sure you have everything in parentheses. Okay, negative 2.6, not minus 2.6, but the negative on the bottom. All right, times 10 to the symbol, all right, caret, and now it's negative 6, so we got to use negative 6. Close it. Next exponent, 3.8 times 10 to the negative 6th. Close it. All right, all that is on top. I hit equals. And then I'm going to divide that all by the bottom value of 0.75 squared. Close it. And boom. We get a value here of negative 0.158. If you rounded it to 2 decimals, you could put 0.16, but I'm going to leave it at that, and that will be in newtons.
I'll make 2 copies when I'm done. Don't worry about
All right.
copying that.
So now you guys are going to pretty much finish out and solve for 13. Okay? You're going to finish out and solve for 13. All right.
Can I run into, just make a copy of these 2 really quick for him?
Mm-hmm.
Thank you.
Mm-hmm.
It's this one and it's this one. Yes.